acid-base balance, and particularly arterial blood gas interpretation, have the reputation of being complicated and difficult to understand. But we're going to make it simple and fun. You might even enjoy it. ABGs, or arterial blood gases, are one of the most important indicators of a patient's acid-base balance and oxygenation. To be able to interpret blood gases, you must first have a basic understanding of acid-base balance. The hydrogen ion is the building block of the body's acid-base balance. The hydrogen ion controls the acidity of the solution. The pH is the measurement of the concentration of the hydrogen ion in extracellular fluid, in this case, the blood. Because it is a negative logarithm, pH increases or becomes more alkalotic as the hydrogen ion concentration in the blood decreases. Conversely, pH decreases or becomes more acidic as the hydrogen ion concentration increases. The normal pH of blood is 7.35 to 7.45. Any variance from this narrow range results in a patient being in an uncompensated state. This can cause potential problems for the patient, from mild all the way up to life-threatening complications. A patient with a pH below 7.35 is said to be in a state of acidosis. In contrast, a patient with a pH above 7.45 is said to be in a state of alkalosis. The body, when functioning normally, can maintain a normal blood pH of 7.35 to 7.45 by means of its internal buffer system. The buffer system acts as a defense mechanism that responds to changes in the hydrogen ion concentration so that the blood remains in the normal 7.35 to 7.45 range. The primary buffer system affecting serum pH is the carbonic acid-bicarbonate relationship. The free hydrogen ion combines with the bicarbonate to form carbonic acid, which then breaks down into water and carbon dioxide. The water can then be excreted by the kidneys, and the carbon dioxide can be exhaled by the lungs during respiration. In order for this buffer system to work, the pulmonary and renal system must be functioning properly. Any disturbance with the lungs or kidneys can upset this delicate balance and result in a state of acidosis or alkalosis. In addition to the pH, other values are utilized in measuring ABGs. These include PCO2, which is the measurement of carbon dioxide in arterial blood, HCO3, which is the bicarbonate in the arterial blood, PO2, which is the measurement of oxygen content in arterial blood, and O2 sat, which is the percentage of hemoglobin saturated with oxygen. The O2 sat is vital in assessing the oxygenation of the tissues. A normal PCO2 is 35 to 45 millimeters of mercury. A PCO2 below 35 is alkalotic, and a PCO2 above 45 is acidotic. Don't get confused. You may think this is backwards, but it's not. An increase in PCO2 leads to an increase in hydrogen ion concentration, which causes the pH to fall. Therefore, an increase in PCO2 leads to a decrease in pH. Conversely, a PCO2 below 35 is alkalotic because there are fewer hydrogen ions. This causes the pH to rise. A normal bicarb, or HCO3, is 23 to 27 milliequivalents per liter. A bicarb value below 23 is called acidotic, and a value above 27 is called alkalotic. This one's easy to remember. It moves in the same direction as the pH. Below normal values means acidosis. Above normal values equals alkalosis. A normal PO2 is 80 to 100 millimeters of mercury. Meanwhile, a normal O2 sat is 96% to 100%. We've discussed acidosis and alkalosis. Now let's broaden that to include all four abnormal acid-base disturbances. These include respiratory acidosis, respiratory alkalosis, metabolic acidosis, and finally metabolic alkalosis. The respiratory disturbances, as their name indicates, have to do with altered ventilation. In turn, metabolic abnormalities are non-respiratory in nature. Metabolic problems can be caused by poor renal function, diabetes, shock, excessive vomiting or diarrhea, large amounts of nasogastric drainage, or fluid and electrolyte imbalances. When these abnormal states occur, the body tries to compensate, striving for a state of equilibrium. The lungs can begin compensating immediately. However, the kidneys, which are the controlling mechanism for metabolic compensation, are much slower to react. They start compensating within 24 hours, but may take up to 5 days to reach their maximum potential. Even with these mechanisms in place, the body may not be able to attain equilibrium. Now for the fun part, the family tree of an ABG, or Name That Baby. First, start by writing down these normal values. pH, 7.35 to 7.45. PCO2, 35 to 45. HCO3, 23 to 27. These lab values will be used to determine whether your patient is in respiratory acidosis, respiratory alkalosis, metabolic acidosis, metabolic alkalosis, or a normal state. As we said earlier, this is called the family tree of an ABG. Each ABG has a first name, a middle name, and a last name. Think of it as you would naming a baby. The first name only has two choices, compensated or uncompensated. The last name also only has two choices, acidosis or alkalosis. The middle name has more choices, so we'll save it for last. The pH always determines the baby's first and last name. In this example, the pH is 7.23. Is this normal? If it is, the baby's first name is compensated. If it's not, the first name is uncompensated. So what is the first name? Right, uncompensated. Next we'll choose the last name. Is the pH acidosis or alkalosis? If you said 7.23 is acidotic, you're right. The baby's last name is acidosis. So now we have a first name of uncompensated and a last name of acidosis. How do we determine the middle name? We're going to determine the baby's father. Look at the CO2 value of 32. Is that acidotic, alkalotic, or normal? Refer to the normal values that you wrote down. It's alkalotic, so write down alkalosis beneath the 32. Next, look at the HCO3 value of 14. Is it acidotic, alkalotic, or normal? It's acidotic, so write down acidosis underneath the 14. Now you have alkalosis under CO2 and acidosis under HCO3. Refer to the baby's last name. What was it? It was acidosis. The father of the baby will have the same last name as the baby. Where do you find acidosis? Under CO2 or HCO3? Right, under HCO3, which is metabolic. So write in metabolic for the baby's middle name. His name is uncompensated metabolic acidosis. Remember, CO2 represents respiratory and HCO3 represents metabolic. Wasn't that easy? Let's try another. In the next example, the pH is 7.10. Is the baby's first name compensated or uncompensated? You're right, it's uncompensated. Now his last name. Is it acidosis or alkalosis? The pH at 7.10 is acidotic, so baby's first name is uncompensated and his last name is acidosis. Now let's choose his middle name. Go back to the lab values. The CO2 is 63. Is that acidosis or alkalosis? Yes, it's acidosis, so write that under the value of CO2. Next, look at the HCO3, which is 28. Refer back to your normal values. Is that acidosis or alkalosis? It's alkalosis, so write alkalosis under the HCO3 value of 28. Now you have acidosis under CO2 and alkalosis under HCO3. Refer to the baby's last name. What was it? It was acidosis. Who is the baby's father? The father of the baby will have the same last name as the baby. Where do you find acidosis? Under CO2 or HCO3? Right, under CO2, which is respiratory. So write in respiratory for the baby's middle name. His name is uncompensated respiratory acidosis. You're on a roll. Let's do the next one. The pH is 7.51. Is this normal? No, so it's uncompensated. The baby's first name is uncompensated. Now his last name. Is 7.51 acidotic or alkalotic? Yes, it's alkalotic, so baby's last name is alkalosis. Now let's find his father and choose his middle name. The CO2 value is 28. Look at the normal values that you wrote down. Is CO2 acidotic, alkalotic, or normal? Right, it's alkalotic, so write alkalosis under the CO2 value of 28. Next, look at the HCO3, which is 25. Is this acidotic, alkalotic, or normal? It's normal, so write normal under the HCO3 value of 25. Refer back to the baby's last name. What is it? It is alkalosis. Who is the baby's father? Remember, the father of the baby will have the same last name as the baby. Where do you find alkalosis, under CO2 or HCO3? Right, under CO2, which is respiratory. Fill in respiratory under the baby's middle name. So the baby's full name is uncompensated respiratory alkalosis. Let's keep going. It's fun to name these babies. In this example, the pH is 7.54. Is this normal or not? It's not, so this is uncompensated. Write uncompensated under baby's first name. Is the pH of 7.54 acidotic or alkalotic? Right, it's alkalotic, so write alkalosis for baby's last name. Now let's find his father and choose the baby's middle name. The CO2 is 44. Look at your normal lab values. Is 44 acidotic, alkalotic, or normal? It's normal, so write normal under the CO2 value of 44. Now look at the HCO3. It's 35. Is this acidotic, alkalotic, or normal? It's alkalotic, so write alkalosis under the HCO3 value of 35. Refer back to the baby's last name. It is alkalosis. The father of the baby has the same last name as the baby. Where do you find alkalosis, under CO2 or HCO3? Right, under HCO3, which is metabolic, so fill in metabolic for the baby's middle name. Therefore, the baby's name is uncompensated metabolic alkalosis. In the next set of values, the pH is 7.36. Is that normal or not? Yes, it's normal, so write compensated for the baby's first name. Now, because this is in the normal range of 7.35 to 7.45, it's not actively either acidosis or alkalosis. However, it is much closer to the acidotic side of normal at 7.36. The body compensates, but it very seldom overcompensates. So because the pH is on the acidotic side at 7.36, the baby's last name is acidosis. Now let's identify the baby's father and choose his middle name. The CO2 is 55. Is this normal, acidotic, or alkalotic? Yes, it's acidotic. So write acidosis beneath the CO2 value